Okay, guys, I'm happy to tell you that the integration madness is over. You don't have to worry about dealing with tough integrals for a while. We are going to completely change topics over to Chapter 8, which is on infinite series. And specifically, 8.1 is on sequences. The difference between a sequence and a sequence is just a pattern. 2, 4, 6, 8 is a sequence. 2 plus 4 plus 6 plus 8, that's a series. So when we start adding up the terms, that's a series. But for now, we're just dealing with sequences or patterns. Just to start with the basics, I'm going to get as far as I can in a reasonable amount of time on this video. We might take a couple days to do this section because we have the time. But basically a sequence is a function whose domain is positive integers. Okay, so you've been dealing with functions since Algebra 1 or whenever, linear equations or quadratics or whatever, the functions you've dealt with, but normally the domain isn't restricted. You can plug in all the values for x, all real numbers, but now you're just allowed to plug in 1 and 2 and 3 and so on. So your graphs, for example, a function you would have dealt with in Algebra 1 is 2x plus 1. Okay, and you would have graphed that by going to 1 and with a slope of 2, up 2 over 1, connecting the dots. This would have been the function 2x plus 1. Okay, the sequence a sub n equals 2n plus 1. That's the same thing. It's just that we don't plug in any of the negative values down here, and we don't plug in anything in between 0 and 1. And actually, sometimes we'll plug in 0 in certain cases, but by definition, it starts at 1. So we plug in 1, and then we plug in 2, and we get a sequence of dots instead of a straight line. So that graph, let me just redraw that graph. It can be only over on the right-hand side. It might go into the negatives, but this particular one will not. This graph would be 1, 3, and 2, 5, and just the dots instead of the lines. So nothing in the negatives and nothing in between are positive integers. And if you will look at your calculator, pause and grab your calculator if you have it nearby. When you go to mode in your calculator, there's a lot of stuff in here you've probably never used. But for me, the fourth line down, I've got function, parametric, polar, and sequence. I'm going to change my mode to sequence. And when you do that, you are, let's see, from there go to Y1. You can see this menu looks very different. Instead of plugging in y equals in terms of x, it's using u instead of a, or it's using u, v, and w to name the sequences, but it doesn't really matter what those names are. But I set my first one to have a minimum n value of 1, and I did 2n plus 1. Okay, so notice as you're typing this, the X button that you normally use now will produce an N because you've changed your mode. So if you ever wondered why there are 4 symbols on your X button, this is the reason. And we'll get to those other 2 symbols in the next chapter. And then if you just go to your graph and your zoom is what it should be, you get that sequence of dots. Mine almost looks like it's curved, but that's just because the graphics are no good. But I just get this sequence of dots. That's what I get when I plug in 1 into the function and 2 into the function and so on. If you go to your table, you can get values as high as you want to get. And this is obviously a basic linear sequence. We're adding 2 every time that corresponds to that basic linear function. So we'll deal with more complicated sequences than this one. Okay, so back to our notes. One of the first styles of problems is just going to ask you to find the first 5 terms of a sequence. So let's just start with something like a sub n equals -1 to the n plus 1 times 2 over n. And all this negative 1 to the n plus 1 does is it makes your terms alternate. Okay, when n equals 1, I get a sub 1 equals negative 1 to the 2 times 2 over 1. Just plugging in 1 for n. And I get negative 1 squared, which is positive 1 times 2 over 1, which all just simplifies to a 2. A2 is going to be negative 1 to the third times 2 over 2. So that negative 1 to the third makes it negative. This part of the expression right here does nothing but make your terms alternate sign from plus to minus. It doesn't affect their magnitude or how big they are. It only makes them plus or minus. And once you know the pattern is plus, minus, you can just keep switching that over. A3 is negative 1 to the fourth. Again, that's just going to make it plus 2 over 3. So that's positive 1 2/3. All right, and you can, I'll finish the 5 terms the long way, but once you get patterns, you don't have to write it out this way every time. Negative 1 to the fifth is going to be negative 2 over 4, 1/2. And then the fifth term, negative 1 to the sixth, makes it positive 2 over 5, 2/5. So our pattern, this sequence, is 2, negative 1, 2/3, 2/4, which we make a half, 2/5, 2/6, which we make a third, 2/7, oh, I forgot my signs, negative 1/2, and negative 1/3. So it's basically 2 over 1, 2 over 2, 2 over 3, 2 over 4, and alternating plus and minus. So that's one of the first things you have to be able to do in this section, is just evaluate. And this is no more than plugging in x and getting y like you've been able to do for years now. Okay, so let's talk about another kind of sequence, a recursive or a recursively defined sequence. This is the type of sequence where I'll give you something like this. A1 is equal to 4, and a k plus 1, notice you can use k or n or whatever, it doesn't matter, is equal to k plus 1 over 2 times ak. Recursively just means that we are going to determine what I would call the next term based on the current term. Okay, so if you know the first one, you can find the rest based on it. You don't necessarily, I'm not able to say, okay, what if k is 20? Well, I don't know what A21 is because I don't know what A20 was. I can't find the 20th term without knowing the 19th term and so on. But if I do know A1 is 4, then A2, when k equals 1, that would produce A2 because k plus 1 would give me, when k is 1, that would be 1 plus 1 over 2 times ak. In other words, my second term is 1/2 times my first term, because that specifically should be k equals 1. So if A1 is 4, then A2 is 2. Okay? And my next term, when k is 2, A3 is going to equal 2 plus 1, or 3/2, times A2. All right, 3/2 of A2 is 3/2 times 2, which is 3. Okay, so basically, long story short, each term depends on the term in front of it, and it's based on this formula. Probably the most famous recursively defined formula you fans of Da Vinci Code is the Fibonacci sequence. Okay, and the Fibonacci sequence is defined as A1 is 1, A2 is 1, and AN is equal to AN minus 1 plus AN minus 2. So the current term is equal to the previous term plus the term that was 2 terms ago. So I know my first two are 1, and then the third term is the previous plus the 2 times previous, which is 2. And then my next term is the sum of the previous 2 terms, and so on. So this is the Fibonacci sequence. All right, and it shows up lots in nature, and we'll talk about it sometime. But that's an example of a recursively defined sequence. It's based on the terms that come first. Okay? One more little thing I want to discuss with you is factorials, because a lot of our work with sequences and series will involve factorials. Okay, factorial means take the number, multiply it by 1 less, multiply it by 2 less, multiply it by 3 less, all the way down to 1. So 5 factorial just means 5 times 4 times 3 times 2 times 1, which I believe is 120. Factorials get really big really fast. An important thing we're going to learn in this section and in the upcoming sections is how to take limits. Okay, and you've learned limits. You learned at the beginning of Calc 1 that a limit is basically, and in this case they're going to be mostly as x goes to infinity or n goes to infinity. Are these terms approaching as n gets really, really big? There are options for how to take these limits, but basically it's just the same as taking a limit of a function. So the start of Calc 1, when you learn how to take limits of functions, this is the same as that, because these are functions. It's just, what are these dots approaching instead of what's this line approaching? So one quick limit example. A sub n equals 5 minus 1 over n squared. So you could expand this out and see the terms and write out a few terms of it, but really you're just going to rely on your limit-taking skills. So this is kind of connected to our improper integrals. What's going to happen as n gets really, really big? Well, in this case, the limit as n goes to infinity of a sub n is going to be basically 5 minus 1 over infinity, because you just sort of plug in infinity and see what happens. Well, 1 over infinity is nothing. 1 over a billion is basically 0. So you can just try kind of billions, millions, and see what you get. But this essentially equals 5, which just means this sequence, plug in as big a number as you can think of, and it will be really close to 5. It will never quite get to 5 because this will never really get to 0, but it approaches 0. And so therefore our limit approaches 5. Our limit is 5. And the last thing, I promise, this is a young coined term, the hierarchy of domination. You're going to do limits where you have both the top and the bottom approaching infinity. Let me find a quick example. Okay, like, for instance, a sub n equals 2 to the n over 2n plus 1. So if you're taking the limit, you plug in infinity, and basically you get infinity over infinity. And if you remember L'Hopital's rule, you could use that and take some derivatives. But really, if you rely on the hierarchy of domination, you'll be able to to solve these really quickly. The limit as n goes to infinity of this particular sequence is infinity over infinity. And that doesn't mean anything. And it definitely does not mean 1. A lot of people see that and think, well, it's something over itself. It's got to be 1. But this is not equal to 1. So what you have to do is determine which one of these infinities will dominate the other infinity. And there you turn to the hierarchy of domination. Okay, so the bottom is linear. It's growing to infinity, but it's doing something like this. You know, it's growing 2 every time, and so my dot should be steeper than that. But it's growing in a steady fashion. The top is exponential. It grows like this. Exponential will dominate linear. All right, exponential gets up there quickly. So as time goes on, I'm going to have something really, really huge over something that's just regular huge. And they're both getting to infinity, but the top is it's separating itself from the bottom as time goes on. So without further ado, linear, actually, let's put logs first, because logs go to infinity, but they do so very slowly. They go like this. They grow less and less. Linears grow at a steady rate. Powers, like x squared, they go like that, like a parabola. And it doesn't matter if it's x squared, x to the 4th, or whatever. Exponentials, they act sort of like powers, but they go really steep. So they dominate powers in the long run. All right, if you don't trust me, do 100 squared and do 2 to 100th power and see which one's bigger. Okay, and then finally, what I started all of this with is the factorials. Okay, factorials dominate them all. I don't even really have a graph. It's going to look the same as these graphs. It just gets really big, really quick. Okay, because, you know, just try a few factorials. Do 6 factorial, 7 factorial, 8 factorial, and just see how big they are. So long story short, we can tell that this limit is going to be infinity because the top dominates. The exponential on top dominates the linear on the bottom, and we can just declare that limit to be infinity. Okay, I've talked longer than I wanted about this section, but I wanted to get the hierarchy out there. And we will discuss it some more in class and do some practice. And we'll finish up this section in the next video. All right, have a good one. This is Young out.